Okay, in this video we're going to talk about electric field. And so I have Q1, which is here, and it's a charge of 1 times 10 to the negative 9 coulomb. I'm going to try to find the electric field at P1 and P2. P1 is 1 meter away and P2 is 2 meters away. And just to remember, this is the equation for electric field. And so the electric field at P1 equals K, 9 times 10 to the 9, Newton meter squared per coulomb squared, times Q, which is in our case 1 times 10 to the negative 9 coulomb, divided by R squared. R is 1 meter, and square it, and that'll give us 9 newtons per coulomb. Let's look at the units here. The units are just interesting to look at. So what it's saying is that because Q1 is here, if there is a charge at P1, for every coulomb of charge that it has, it will experience 9 newtons of force. Okay, let me say that again. So if you are a charge and you are at P1, you will experience 9 newtons of force per coulomb of charge that you have, right? Because the more charge you have, the stronger the force between you. But we can still use it. It's still a valuable number. Even though it doesn't tell us the force, it gives us an idea of how much force a given charge will experience, compared to other locations in space. So let's just compare it to P2. So the electric field at P2, K, again, 9 times 10 to the 9, Newton meter squared over coulomb squared, times Q, 1 times 10 to the negative 9 coulomb. And now it's divided by 2 meters squared. And that gives us 2.25 newtons per coulomb. And you can see that at P2 the electric field is weaker because it gets weaker as you get further away. And it's also good to note that this is inverse square, just like gravity. So if you double the distance, you get 1/4 of the, in this case, electric field. And so what this is saying is that, say I have a charge at P1. It will experience 9 newtons of force per charge that it is. If we put it at P2 instead, it would only experience 2.25 newtons of force per charge that it is. Right? So this is a way for us to kind of compare different locations in space. Right? Remember, there's not even a charge here in our picture, but there's still an electric field there. And it's just a good way of thinking about it. And the other important thing to notice is that by knowing the electric field, you really do not know how strong the force is, right? To get the force, you've got to multiply the electric field by the charge that's placed there. And that's kind of what these units tell us too, right? So if I put a 2 coulomb charge there at P1, it'll experience 18 newtons of force, right? Because it's for every coulomb of charge you have, you get 9. And again, we just see that by multiplying the charge, 2 coulomb, times the electric field, 9 newtons per coulomb. These guys cancel, and we're left with 18 newtons. I could also say, well, if I put a 1 coulomb charge there, the force would be equal to 9 newtons. And you guys can do that math. But let's say we did the same thing at P2. So if I put a 2 coulomb charge at P2, I would get a 4.5 Newton force. If I put a 1 coulomb charge there, I would get a 2.25 Newton force. And so you see that the electric field tells us kind of if for a given charge, will it be strong or weak? But it doesn't tell us exactly what the force is.